dynamic programming interview problems from LeetCode and from like other resources. And I will be kind of walking you through the process of thinking about dynamic programming problems and understanding how to actually approach dynamic programming problems in when you are solving them in an interview, how to talk through them and how to sort of solve them. And the reason why I'm doing this is because I've often seen people get scared of dynamic programming, and it is a difficult topic to wrap your head around at the start. But you will realize as and when you start doing it, it is actually it is difficult. It is not easy, but it is logical. So if you develop your logic and you fit it around dynamic programming, then you should be able to basically do the problems correctly. So I will be going through some dynamic programming problems, and we will go ahead and just walk you through and just solve the problems, and hopefully we learn something from it. So I will just get rid of all of this previously written code. I have already solved this problem first, just so that I can kind of walk you through slightly better. So this is the LeetCode problem known as climbing stairs. You can find it on LeetCode. It is, I don't know which company has asked it. Okay, so it is an Amazon coding interview problem. However, this is a very classic problem, so do not expect that you will be seeing this problem asked in a Amazon interview now, but you will definitely maybe be asked some dynamic programming problem, and it's good to know how dynamic programming works. It's definitely very, very important. So let's just jump right into it. So I'm assuming you already have familiarity with recursion when I'm doing this, and I'm assuming you already have familiarity with how dynamic programming works. I will just be walking you through the thought process that I use when I'm solving dynamic programming problems. So it's more of a video meant for that. So the question is, you are given an integer n representing the number of steps to reach the top of a staircase. You can either climb one or two steps at a time. Return number of distinct ways to climb to the top of a staircase. So we are given only one thing, which is the number n, which is the height of the staircase, which is where we want to reach, and we are starting from point 0 and we want to reach point 2. Now the way it is we can either go from 0 to 1 or 0 to 2, and then so on and so forth, and then we just want to count. So that means that if we are initializing now, first of all, you need to understand when can you use dynamic programming. So this is something that you will probably develop a lot more with practice. It is something that just intuitively should strike that okay, this problem might be a dynamic programming problem, or this problem might be a graph problem, or this problem might be something else. So that it should be intuitive, and sometimes it's hard to know that, but at the start the way I recommend is you should look at every problem as a DP problem and try to come up with a DP solution to it. If you realize quickly, fail quickly. So when you are coming up with your DP solution, if you realize that the time complexity might be too large, or maybe the transitions of the DP will be very complex and unnecessarily complex, then you quickly realize that okay, there is probably some better way to solve this problem or some alternate way to solve this problem, and then you want to kind of shift over your thought process. At least when you are a beginner, you should do that. Even I do that today. I'm not an expert on DP in any way, but just saying. So okay, so in this case, we are not going to optimize our DP solution a lot. I'm mainly going to focus on because we can do this in O of 1 space also, but for now we will do it in O of n space. So over here, what we are gonna do is we first need to initialize a DP array. But what exactly will the DP array store? So you can see here we have to return the number of distinct ways to climb to the top of the staircase. So that means the DP of I should store number of ways to get to step I. So this is the first thing you have to see. One, what is going to be the dimensionality of your DP? You quickly realize that in this case, this is the only thing I care about. So, and everything is getting stored in just one dimension. So that's great. So you just need this one thing. You only need DP of I, and that's it. So it's number of ways to get to step I. But now let's look at exactly the main thing, the actual update of your DP. So so how exactly does that work? So let's look at it. So how do you get to step I? This is the first question I am going to ask you, and I want you to take your time and think of how you can actually get this. So how exactly do you get to step I? Well, you step up from some step that was below step I. More specifically, you have two options. You either step up from step number I minus 1, or you step up from step number I minus 2. That is the only two options you have. You cannot step up from I minus 3, or you cannot like step down from I plus 1. You do not have any such option. So you only have these two options, and only via these two options can you get this. So that means that dp of I should simply be equal to dp of I minus 1 plus dp of I minus 2 plus 1. It should really just be this much. So here we can just say dp is equal to, and we just say 0 times n, and then we can just say that dp of 0 is equal to 1, and dp of 1 is equal to 2, and we just want to return dp of negative 1, and if len of dp is greater than 2, then we can just do for I in range 2 to n, dp of I equals dp of I minus 1 plus dp of I minus 2 plus 1, and then we can just return this, and you will realize that this should work. Okay, we have a slight problem over here. I'm sorry, we actually, i'm I'm such an idiot. We don't even need a plus 1. Why was I doing the plus 1? I'm sorry, I just sort of confused it with some other problem. Yeah, so we can now just submit. Distant x. Okay, so this is not really an error. We just, apparently the constraint was, yeah, so it could also be just of length 1. So if n is greater than 1, I mean, why would they do that? And else we can just return 1. I don't really understand why you would want to have a constraint of 1. But there you go. As you can see, our answer is successfully accepted for this problem. Now actually I'll also go through the optimization for this. So now I want you to look at this very very carefully, because this is kind of this is what you can do in a lot of DP problems. Let's look at dp of I. Like I said, dp of I is obtained by adding these two elements, dp of I minus 1 and dp of I minus 2. But you quickly realize so that when I'm at dp of I really do not care of dp of I minus 3, dp of I minus 4, anything like that. So I only care about the previous two elements in order to update the current element. And this means that really this is just something that you can do in of one time, and I won't go to the solution. I'll leave that as an exercise to you guys. But basically this means you can simply keep track of these two variables and keep on updating them in order to get dp of I. You will have, if you want the solution, I already have this. I'll just show you guys my solution. I have done that. So this is the solution, and I would recommend you first try it out by yourself, and if you can't, then you check out this solution. And yeah, so just go through that, but I wouldn't recommend you check it. You try to do it by yourself. So this is a very standard DP problem, but it is a very good DP problem, mainly because this problem really teaches you the basic of DP, like the very core of DP. And if you don't learn this, then you will have a lot of problem learning some of the more advanced problems and stuff like that. So now let's look at something like house robber. This is another very standard DP problem. It is a medium problem, so it is certainly slightly harder than your easy problem, but this is also again a very very standard problem in competitive programming, in dynamic programming. And basically this follows another type of dynamic programming where you are trying to optimize something. So yeah, and let me just, I might need my iPad for this, so just give me a quick second. I'll just boot my iPad up real quick, and just a second. All right. Okay, I think I can keep this much. Actually, no, I will keep this much. These are just the two base cases. I will keep these because I don't want to write everything again. So let's read the problem. You are given an integer array nums where nums I represents the amount of money in ith house. The houses are arranged in a straight line. That is, the ith house is the neighbor of I plus 1 and I minus 1th house. You are planning to rob money from the house, but you cannot rob two adjacent houses because the security system will automatically alert the police if two adjacent houses are broken into, return the maximum amount of money you can steal, and not alert the police. So, fairly straightforward to understand. Basically, you can see over here they have kind of walk you through the test case. You, in this case, you can either rob this or this, or you can rob like this or this, but you cannot rob the two threes because then the police will get alerted. And yeah, in this one also they have robbed the following, and yes, so that is pretty much it. So now I want you to again pay close attention to the problem and look at my approach. So okay, let's actually, the way I like to do this is sometimes copy paste the example and run through the example. So let's say I rob this house, then I cannot rob uh, this house because the police will get alerted. In which case, I will have to rob this house, which is the 8th house, because only then the police won't get alerted. So, this is kind of how you can work. Basically, you have a choice. In these three houses, you can either rob this house, which is your middle house, or you can rob the two extremes houses. And the way you can maybe think about it is, let's say you are at house I. So let's say you are at house 8. You have an option to rob 8 and 2 or rob 9. In this case, you want to rob 8 and 2, but maybe in some other case, you might want to rob 9. And that is literally all you have to do. So that means that your dp of I stores the max amount of money robbed until house I. So then what you can say is that dp of I should just be max of dp of I minus 2 plus dp of uh, plus nums I comma dp of I minus 1, and this should do the trick, and then return max of dp. So you just do dp is equal to 0 times len of nums, and now you have to set some and then we can just do for I in range, and you want to start from now dp of what is going to be dp of 0, what is going to be dp of 1. So that is what you need to think first, is what is going to be dp of 0, because if you see this, then this is kind of how we are working, and so it gets a little like tricky in that way. So dp of 0 is just going to be nums of 0. dp of 1 should be max of nums 0 nums 1, I think this is correct, and then for I in range 2 to len of nums dp of I and you can see it is accepted there and it is accepted here also, and you can kind of understand why this is working. So this is a very standard problem, like I said, but as you can see, this is an important problem and it kind of shows you how you can approach dp problems. So now let's go on to LeetCode and just solve some random good looking dp problem. I'm just thinking of a good one that is maybe a little bit less standard. I want to do a less standard DP problem because I'm sure you will find like standard DP problems in many places, but non-standard DP problems are generally going to be a little better. think this perfect squares might be a good one. It's 55% acceptance, so it's medium acceptance, and overall it should be maybe good. I think so. Okay, apparently I had already approached this problem previously. I'll tell you, I have absolutely no recollection of this. So, yeah. Oops. Okay, let's read through this problem. Given an integer n, return the least number of perfect squares numbers that sum up to n. Least number of perfect square numbers that sum up to n. So there is a greedy element to it because we want to minimize that, but we will definitely need some dp. A perfect square number is an integer that is the square of an integer. In other words, it is the product of some integer with itself. 1, 4, 9, 16 are that, but 311 is not. Okay, great, I understand. Okay, so uh, okay, great. And we have to return the least number of perfect square numbers that sum up to n. Okay, so we maybe initialize a dp array of size n. dp of I stores the min number of sum to reach the value of I. And in terms of constraint on n, you can see n is a very small constraint, and since we are only summing square numbers, that means if we have pre-computed all the square numbers up until 10 to the power of 4, we can simply have an O of 1 constant time execution in order to uh, in order to kind of understand what you can have, what you can't have, stuff like that. So yeah, that's kind of what I'm gonna be doing. So pre-compute the squares from the start. Okay, now this problem is actually very similar to another problem which now that I'm writing this down, it appears to me that this problem is actually a very similar problem to another very classic DP problem known as the coin change problem. And I'm sure a lot of you might have already heard of that problem. It is a very classic kind of a problem in dynamic programming, which which is very integral to dynamic programming. So it's a great thing that I chose this problem to solve, because it is, it kind of teaches you the most important things. Just a second, let me have a sip of water. Okay, so let's actually work on this now. So we pre-compute the squares from the start. Now let's say I am at dp of I. How can I get to dp of I? Let's think about it very carefully, and you will quickly realize it's actually very much doable. At least I think so. I mean, so I can get to dp of I by adding 1, 4, 9, 16. So I can get to dp of I from dp of I minus 1, or dp of I minus 4, or dp of I minus 9, or so on and so forth. So basically, as long as you are at a value greater than 0, I minus x is greater than 0. So as long as I minus x is greater than 0, dp of I equals max of all those, is equal to min of all those values. And you quickly will realize exactly that this is all you need to do. What we also can do is we can just pre-fill those particular elements, like the 1, the 4, the 9 and 16, blah 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 blah, with like the numbers, but we don't actually have to do that, because this condition checking that we are doing will sort of take care of all of that. So now you can quickly realize it is so simple to actually solve this problem. It's actually a very easy problem to solve. if you just develop this intuition of doing this. Now, one little thing I would like to tell you, this particular thing I'm doing is known as pull DP. Pull DP is basically when you look at the previous states in order to determine the current state, which is how we did the house robber problem also. We looked at I and I minus 2 and we compared it to I minus 1. However, there's also a thing known as push DP where you look at the current state and instead of doing the I minus 1 or I minus 4 or I minus 9, you do I plus 1 or I plus 4 or I plus 9. It's the same thing, it's just done slightly differently. I am a little bit more of a pull DP fan. Like, I like to use that a bit more often because I find it to be slightly more intuitive and I am able to work with it slightly better. So I tend to use that. But push DP also works just as well. So if you are a little bit more comfortable with that side, I'll leave that as an exercise for you if you want to go ahead and uh, solve that. And currently we are only doing 1D DP, but maybe in the future video I'll also do like 2D DP and stuff like that, and like more dimensions, and maybe do some more advanced DP problems. So yeah, so for now let's just initialize our DP array. So DP is equal to, we are going to initialize it with 0 and we are going to initialize n elements. Now what exactly, now we also first need to pre-compute the squares. So we pre-compute the squares. So we do for I, actually no, we do something like this: idx equals 1 while idx star star 2 is less than n, less than equal to n, squares dot append idx and idx plus equals 1, and we can just do this. Great. So now we have our pre-computed squares. It's very simply done, nothing too crazy. So now what we can do is we can now just set some of the more basic constraints. So dp of 0 is gonna be equal to 1, since there is only one way to form that. And yeah, that's pretty much all we need to do. And if len of dp, actually not len of dp, yeah, if n equals 1, we go from 1 to n. Now here's where important stuff comes in. We do okay, what do we do now? Basically I understand what I have to do. I'm just trying to think of a quick way to do it. We need to do this I minus stuff. Best thing is that squares is going to be tiny, so we don't have to worry about that. Reason I say that is because if you think about it, 10 to the power of 4 is 10,000, and if you take root of 10,000, it's really just going to be 100. So the max len of squares is going to be 100, and 100 is a very small constant factor, and we can deal with 100 very easily. So that's great. So here, when I am at I want to check if, so I can just do for s in squares. Maybe I want to do x. Let's use x. If I minus x is greater than 0, greater than equal to 0, then we can just say and what do I want to do, we can just take there we go. We just do this and we just do min val equals min of min val and dp of I minus x plus 1. So this is all we need to do, and then we just do dp of I equals min val, and then we just return dp of -1, and that should do the trick. Ooh, it doesn't do the trick. Okay, so we are getting off by 1. Why are we getting off by 1? Or is it just off by 1 in this, and like, wait, Okay, no, it is not off by 1. This is off by 2. What am I doing wrong? Probably some small error. 4x in squares. Okay, maybe I think that's what it is. Not sure. There is another problem. We have to check I plus 1. That's the first problem. We have to check I plus 1 every time. Uh, so that's that. Am I sure? Yes, I am sure. Yes, I have to check I plus 1. Maybe it was just that. Yes. So there it was a very tiny mistake. I don't know why. Because remember when we were doing that, so it's 0 indexed in programming, but we were doing 1 index stuff. So it sort of it messed that up. But there we go. As you can see, our code is now accepted. And yeah, I mean, look, I'm not really gonna be dealing with optimizing like runtime and stuff, because if you look at this technically, we are getting performing average over here, but we are performing very well over here. And to be honest, we are having an O of n solution, and I'm fairly certain you cannot do this in anything less than O of n. Apparently, I guess these guys managed to do it in less than O of n, but yeah, I mean, to be honest, I mean, that's all right. I mean, this solution is also really good. So yeah, this is a good solution. What we have an often solution, and plus, I mean, this was supposed to be a DP problem, and basically, I'm pretty sure if you, let's say, you go ahead and do this in a interview, I'm fairly certain that the interviewer will be okay enough with this solution, and they won't pressure you to come up with more optimal solutions. So yeah, other than that, obviously, this wasn't like for an interview, but I mean just general advice. But obviously, like if you are watching this tutorial and preparing for interviews and stuff, please explain through the thought process, don't just code it out. But yeah, so write stuff down like this, the way I kind of explained. That's very important to do. Have a clear line of communication. And if any of you, and I would like to leave it open to you guys, if you implement this in other languages, and let me know in the comments down below. And if you can also think of any better approach or a push db approach to this, let me know in the comments down below, and go ahead and implement that. Give me the code, give me as a GitHub repository. You can even just drop it down in the comments. Yeah, I'll be okay with that too. And yeah, we can just I'll go through it, look through it, and definitely sort of uh, I'll definitely kind of you know let you know if it's correct and stuff like that. And yeah, I would also like to probably tell you, so there are a couple of cool DP problems that LeetCode has. So go through the tag of dynamic programming, solve some easy and medium problems. Hard, don't do them right now, because if you are watching this tutorial, you are probably really just getting started out with DP. Solve the longest increasing subsequence problem. It is a great problem. It is a very standard problem, but it is a problem that is very good. Also do coin change 1 and 2. That's also two great problems that LeetCode dynamic programming has to offer. And go through CSCS dynamic programming section, because even that is a very good section on dynamic programming. Go through these things, and you will definitely be much more comfortable with dynamic programming than what you are right now, if if you are watching this video. So yeah, that's it for this video, and I hope you enjoyed it. If you did, like and subscribe to the channel, and I'll see you in another YouTube video. Until then, bye bye.